Thank you very much to the organizers, Freddie and Elena in particular, for getting me out here. I'm scratching my head a little bit because I don't do medical imaging and I don't do machine learning. So the question then is, what can I talk to you about? I thought I'd present a little counterpoint to machine learning and keep it a little bit philosophical. I'll make some parts of it concrete. And if I start to run longer than I should, I'll wrap it up quickly. Okay. All right. So the title you can see over there, and the little picture in the corner, I guess if you're from here, you recognize it as the clock tower in Sigiswara. Is that right? Is that how you say it? Okay. The bottom of the screen doesn't show. I have it over there. So that's not quite a mechanistic model. It's a mechanism of some kind. It's a mechanical analog for the rotation of the Earth, I guess, but it somehow evokes mechanistic models for me. I'm very interested in these sorts of things. My co-author and I recently, well, 3-4 years ago now, have a book published that nobody uses except at MIT. We have a different cut through the set of topics that people haven't found interesting to teach. So our students use it and nobody else buys it. So I thought I'd flash it up and make a little advertisement. But the clock there is the old clock in the town square in Prague. Many of you have seen it. And this is an astronomical clock, so it not only represents rotation of the Earth, but it has the position of the sun and the moon and makes references to the zodiac and so on. A nice mechanism there. When we came to the what the publisher calls a global edition of our book, which also doesn't have sales, but it doesn't matter, we picked another mechanism for the cover, and our friends from Holland will know this well. This is from the 1700s, this man who built a planetarium that's, I think, the oldest functioning planetarium anywhere, in the roof of his house, much to his wife's dismay, but he persisted, and it still functions, and it's a beautiful piece. I've seen the clock in Prague. I haven't seen this yet, so I plan a trip sometime. Say that again? Have you seen the wife? Now, the reason he built it is there were 3 planets that were going to be in alignment, and people thought that meant the end of the world. And so to convince them that actually this wasn't something so special, he embarked on this to give people a more concrete feel for how the planets move. This is, I guess, 100 years after Newton. All right, so I unfortunately had to miss some of the talks this morning because after Professor Alex Frangi's talk this morning, I saw that actually he had the figure I needed to tell you what I'm going to talk about. So I had to go back and make the slide. It's not as nice as the one that he showed, but he talked about this pyramid, which in some incarnations is well known, but he added the decision piece at the end and various comments on it. And really, this is a good way to anchor what I'm going to talk to you about. So data we're living with. I think that a lot of the machine learning algorithms are focused on classification. So you give them data and they'll tell you yes or no, or which of a particular class of things something belongs to. So in a sense, the machine learning people who have the information, the knowledge, and the wisdom put a little black box there, and they take you from data straight to decision. And so you in your application domain don't get the benefit of crawling up this ladder. So that I think is a seriously missed opportunity in many situations where you do want to go through these stages, because there's good learning to be had in that way. Machine learning also, I don't think, has quite figured out how to automatically take you through those stages. So I don't think machine learning is giving us the models that I'm going to be talking about, the mechanistic models. What Alex talked about this morning was, given things like Navier-Stokes, the mechanistic model, using that to then make sense of the data and extract information from it in a better way than you would just from the data alone. From the data alone, you're looking for patterns, but if you have a sense of where the data came from, which is what the mechanistic model has, then you can extract more from it because you're learning something about the underlying model as well, not just patterns in the data. A simple paradigm for that is the familiar Kalman filter, right, where you have a dynamic model, you have measurements, and you combine the two. You could have control folded in there too, the linear quadratic Gaussian framework for control, where you're doing that whole loop, and the model is essential to that. But machine learning, I don't think, is the thing that's giving you the model. The machine learning, in the most common application of it, is putting that box there and giving you the answer like an oracle. So that's really what I want to kind of tease out. Now, for me, a mechanistic model, I've had to figure out what that term means to me. I don't think there's standard definitions of it. But for me, I think of it as a representation that's based in terms of components. The components are meaningful in themselves in some fashion. So when you go to the clock tower, the gears in the clock are parts of that process, but they're not very meaningful as representations of anything. They make the mechanism function, but they're not interesting for me as part of a mechanistic model. So for me to think of it as a mechanistic model, I need to be composed of parts that are meaningful in themselves. I need a description of the intersection, interconnection, interaction of the parts. And from that emerges the behavior of the system that I'm interested in. So that's sort of what I mean by a mechanistic model. And so what I wanted to talk about, just to connect this back to medicine now, since I'm not doing imaging, is to tell you about a very simple mechanistic model that actually is very powerful. And I call it profound because you can actually extract a lot from it. In the end, it's just one resistor and one capacitor in the model. But I'm not sure how machine learning, given the 200 years of data that went into extracting that model, would tell you that it's a resistor and a capacitor that you should look for. So that's kind of the challenge. I should confess that a lot of this is from my own ignorance. I don't know the machine learning literature well. It may be that there are people doing this already, but I don't see it in what I read. Okay, so this is a model that goes back to Otto Frank and has been developed since and used since and refined since. So it's unfortunate that you lose the bottom of my slides. I shouldn't have written so close to the bottom. So the rest of the talk will be some of these contrasts. And I'll be happy to stop with that if I run out of time. If there's more time, I'll give you examples beyond the Windkessel to show you again how simple mechanistic models can take you a long way. All right, so the Windkessel model was developed in trying to understand the cardiovascular system. There are many physicians here and medical students, so you don't need to hear this from me, but I'm going to assume that I'm talking to computer scientists maybe who haven't seen this, or electrical engineers, which is the background I come from. And I didn't know any of this till I started working in this area. So we're trying to represent the pulsation of blood through the cardiovascular system. And you know that there's the left heart pumping blood out through the aorta, and it goes through the body, comes back to the right heart, gets pumped through the lungs and back to the left heart. In terms of what you see along the way, this is actually a useful picture. So this is trying to represent, in some sense, what the blood is seeing as it goes through the system, and representing the pressure that you measure at that stage of in the bloodstream. This is not, again, I'm sorry, this is not my figure. The citations are at the bottom there. It's Falco and Neal from 1971. So if you're looking for citations, look in the shadows here. So the main pump in the heart is the left ventricle, which is pumping out the blood. Big pressure variations within the ventricle. When it's contracting, the pressure rises. When it's filling up, the pressure drops. This is stylized, so you should take it with a pinch of salt. But the blood comes out into the aorta, which is an elastic vessel, large diameter. So very little resistance, but some ability to absorb pressure pulsation. So it's a compliant vessel. And then from there, it goes into vessels that are smaller, that present more resistance to the blood flow. So these are the resistance vessels, and therefore the pressure starts to drop because it takes a pressure drop across a resistive vessel to get flow through it. Then you get to these arterioles, which are actually smaller vessels still, but with muscle around them and muscle under the control of the sympathetic nervous system. So the body can actually control resistance to flow by contracting these muscles through the sympathetic system. And then there's the capillary exchange vessels, very small vessels, very many of them. And then you come back now to the venous side. Okay, so this is, and I won't go through all of this, but there's an analogous thing. You come to the venous side, there's the veins, which have different characteristics. They're much more floppy, they're not elastic. And then you come to the right heart, and things get pumped into the lung with similar kinds of structures, and you're back to where you started. Okay? Someone has studied the distribution of these vessels in dogs. I haven't seen analogous numbers for humans, but you get some idea of how this bifurcation happens. The aorta is a large diameter vessel with a particular cross-sectional area, but by the time you get down to the capillaries, you're talking about 1.2 billion capillaries. In aggregate, a much higher cross-section, but each individual one has a very small cross-section and a very small length. And if you work out the velocities, you'll see mean aortic flow velocity is high. When you get down to the capillaries, you're down to 0.4 centimeters per second, and that turns out to mean that the blood lingers for about 2.5 seconds in the capillary. So you can see it's beautifully efficient in terms of pumping the blood around and getting it to interact where it needs to. So are we going to have to model all of this to understand the arterial pulse is the question. And so here's where the aggregation and the modeling art starts, really. Well, it started on the previous slide already. There was a lot of abstraction there. But here we start to think of the system as essentially just having the elasticity of the large vessels, the resistive part, and then the veins, and we'll probably just ignore the veins as well when we get to it. So we're going to aggregate it hugely. Now, before I show you the mechanistic model that an electrical engineer is comfortable with, let me tell you about analogies that actually make it very very nice to work, very feasible to work with electrical circuit analogs, and very nice as a way to think about things for those who think in terms of circuits. Also a very good way to get electrical engineering students into biomedical domains. If you've got an electrical circuit analog for something, you can get them started very quickly. So the analogies are fairly clear. You've got electrical voltage, which is a potential difference. You've got pressure difference. Flow is like current, volume is like charge. You've got the analog of resistance here. Resistance is the pressure drop divided by the flow. For an electrical circuit, it's the potential difference divided by the flow. And there's a very natural notion of a capacitance. Okay, so the capacitance corresponds to volume storage. This is actually an incremental capacitance that I've written here. It's the increment in volume that you get for an increment in pressure. Okay, so you can see that that's a key feature of the large arteries. The small increase in pressure, they're elastic, so they can store more. Okay, so now another one that we've found useful is actually when you get to concentrations, if you're tracking concentrations through a system, you're doing mass balance again, and you are led very quickly again to analog. So there's partial pressure, which is a measure of concentration, functions like a voltage, and mass flow functions like a current. So in systems that involve fluids, flows, various masses, components of flows, with pressures and volumes that you need to track, think of electrical circuit analogs. Okay, as I said, I'm going to ignore the venous side, so we're looking at this picture just on the arterial side. So the left heart pumping into the big arteries and down to the capillaries. And so here's our mechanistic model. Okay. So for somebody who can read circuits, this is very simple. There's a current source here, which represents the heart putting blood out into the system on every heartbeat. We're going to actually model this as a series of impulses, so impulse ejection. Every heartbeat, there's a dump of charge into the system. This is a capacitance, which represents the compliance of the big arteries, and this is a resistance, which represents everything, the effective resistance of everything downstream. The doctors call this total peripheral resistance, or sometimes systemic vascular resistance. So there are a couple of names it goes by. This is supposed to stand for arterial compliance, arterial blood pressure. And what I've shown here is what you might get for a typical measurement of blood pressure, for instance, in the radial artery. And in the purple, what you're seeing underneath is what you would get from this model if you fed it with a series of impulses of current. So every time you dump charge in it, there's a sudden jump of the voltage, and then it decays through this, the voltage on this capacitor decays through the resistor in between, waiting for the next pulse. And you can see you're getting a fairly good representation already. Okay, so I said series of impulses. This is what I mean. This is a Dirac impulse. So it's really horribly idealized. You can refine it if you want, but you're already in the ballpark with the Dirac impulse. And every time one of these impulses hits, that charge gets dumped on the capacitor. It can't go through the resistor instantaneously. It can decay through the resistor, but the immediate effect is felt by the capacitor. So there's a jump in charge, therefore a jump in voltage, and you can relate the two. And you can talk about transients as well. There's a time constant of decay within a beat, and it turns out it's the same time constant essentially that governs approach to steady state as well. Okay, so with just the most basic electrical circuit knowledge, you get things like this. The stroke volume, which is the amount of blood put out per beat, is related to the jump in height of the pressure through this relationship. So pulse pressure is systolic minus diastolic. So 120 minus 80 millimeters mercury typically. So the compliance times that step is the charge. That's just the definition of what the capacitor is. Given that you've dumped SV, the stroke volume's worth of charge on that capacitor, that's the amount by which the voltage will rise. So the voltage rises by the charge divided by the capacitance. What about the cardiac output? The cardiac output is blood amount per beat times beats per minute to get liters per minute or whatever unit you're using. So the cardiac output is heart rate times stroke volume. So it's compliance times pulse pressure times heart rate. So what you see is that cardiac output is proportional to the heart rate at that time times the pulse pressure. And these are very measurable things, right? Systolic minus diastolic you can measure, heart rate you can measure. So you can get something proportional to cardiac output very easily. The proportionality constant is a characteristic of the big arteries, and it's not going to change very much. It may change with age. We don't quite know how it changes, but it's not under sympathetic control. It's not something that varies, so it's fairly constant. The total peripheral resistance, again, thinking circuits, if you've got an average voltage here of AVP, then AVP divided, voltage divided by current gives you resistance, so that's your total peripheral resistance. And you can estimate the arterial blood volume, again, from this relationship. So it's a very simple circuit, and it gives you some insight. And the interesting thing is that physicians actually think in terms of these quantities. There are medications whose intent is to modulate the total peripheral resistance by contracting or expanding these vessels. There are medications whose intent is to reduce the total blood volume. Medications that will try and get your heart rate to slow down or to speed up. Medications that have combinations of these effects. And the effects of all of those in blood pressure can be tracked through this simple model. So it's a very powerful model and very simple. Okay, so I'll just give you a quick illustration of an application we made of it. We were actually, this is some time ago now, this was 2011, some colleagues had built a wearable device that could measure ECG and also had accelerometers on it, so it could measure physical activity. And so that's under the shirt here. You don't see it. What you see here is something that's measuring chest expansion to get respiratory rate. And then he's wearing something called a portopress, which is a finger cuff device that will actually extract for you the arterial waveform without you having to put a catheter in the artery. Okay, so you can get the blood pressure waveform externally, non-invasively. This was actually something developed for the space program, and there are other versions that can be that are used now in other settings, less expensive. Okay, so that's the setting, and then he had 10 subjects go through a series of physical activity, and then the intent was to compare the measurements on the wearable device with the measurements of the lab quality devices. Okay, so you're getting blood pressure here. This is not from the wearable device, that's from the portopress, but you're getting physical activity variations, and this is an aggregate measure of physical activity. It's the root sum of squares of the accelerations on the 3 axes. It's a rough measure, not bad. So you can see here when someone's lying down or sitting or standing, there's really no physical activity. There's activity on the transitions. When they're jumping, there's activity, walking, running. So the red line traces activity. So now let's look to see what happens with cardiac output with that activity. This is a very simple, crude measure of cardiac output. We're getting something proportional to it. And it is exactly what you would expect. When there's activity, the cardiac output increases, and substantially when you're running. And this is under the influence of closed-loop control within the body. Okay, so the body senses the activity, the muscles dilate, there's more blood needed, pressure starts to drop, so there's various things going on to adjust. So our crude measure of cardiac output is actually doing pretty well. And then if you track total peripheral resistance, that's in the green here, you see that that's also doing what you expect. I mean, during physical activity, because of the dilation of the vessels and the muscles to bring more blood to the muscles, there's a decrease of total peripheral resistance, and so there you are. Okay, so very simple model, but that mechanistic understanding is just priceless, really. The question is, you know, with all the data that you could throw at it, would you get this kind of insight from what we know of machine learning models? How would you guide a machine learning model to extract such a model, or machine learning methods? Okay, so I want to go through a little checklist of contrast between the mechanistic model viewpoint and the empirical or phenomenological viewpoint. This goes back to Alex's slide from this morning. Going from information straight to decision, that's the phenomenological route. Going in the other direction is the mechanistic model route. Okay, so this is what I'm trying to contrast it with. And so as I said, when you're thinking mechanistic model, you're trying to isolate all of this. Okay. And it's the interconnection of these parts that's giving you the dynamics of interest. I'm using dynamics in a general sense. I'm not necessarily talking causal systems and so on, but the behavior that emerges from an interconnection of parts. So here's what I see as a key difference with mechanistic models. You're trying to understand the system first, and the answers can come later. You don't start off with a question that says, solve this problem for me, solve it, and then move on to the next thing. You're trying to slowly grow answers through understanding. Okay. I'm caricaturing just to make some of these contrasts, so forgive me if I'm saying unkind things about machine learning and you're deeply embedded in it. Mechanistic models are built up and refined over time. So these models for cardiovascular control, it's many researchers over 100-year or 200-year period maybe, collecting data in their individual labs. And that's big data and aggregate, but that's not how the model was arrived at, by taking all of it at once and doing something with it. So I like to think of it as accretive learning. Accretive meaning adding bit by bit. or slow learning. Nicola talked about slow publishing. This is the other side of it. Slow learning goes with slow publishing. With the model as a substrate. So you can learn in many different contexts for many different problems, many different researchers and labs, but you've got that underlying substrate to bring your learning back to. And the conversation happens at the level of the model. Okay. The mechanistic models are, again, I hinted at that. They're multifunctional. You're looking for them to give you understanding and then solve many problems, as opposed to an algorithm that's going to solve one problem for you. Another piece that I find very interesting here is that mechanistic models give you a way to think of new hypotheses. They suggest things that you might want to try. I don't quite see that in what I see of machine learning. Where's the richness of mechanistic models in suggesting new things to try? I don't really find that. Okay, so mechanistic models are everywhere. It's not just blood pressure. The domain I used to work in, power systems and power electronics, again, that's all about individual components with interesting dynamics, interconnected to give you global system-level dynamics. And you really want to understand it at that level, and then make aggregations, simplifications, and so on, but keeping track of what these are referring to. All right, so what I see is some of the challenges here. If you look at a physiology textbook, it's a very comforting kind of book for someone from control theory or electrical engineering to read, because it's all built around mechanistic models and mechanistic thinking. So what I find myself wondering is, if you take all the learning we're doing from big data and machine learning, how is that going to factor into the next edition of the physiology books? What are you going to be able to take from that and teach to your students about physiology? What's the process for that? I can't quite put my finger on it. And again, this is something I said before, that machine learning is, at least in the situations I've encountered it in, is largely focused on classification, not discovering more about models. Although when it comes to image kinds of applications, people do try and take account of particular characteristics of images, particular characteristics of human vision, and so on. So there's some factoring in of the model. Whoops. What happened there? I went right to the end. Yeah, so here's another thing to chew on. You've done your machine learning exercise with your data and your particular problem. How is what you've learned transmitted to somebody else for them to take advantage of if there's no model to serve as a substrate? So where's the aggregation and the accretion coming from? Certainly the machine learning community within themselves, when they develop methods and approaches to problems, they're doing all of this. They're developing theories for how to approach machine learning, but in the domain that you're interested in for the application, how is machine learning helping you, apart from giving you a series of oracles? And I'm going to get into trouble when I get back to MIT, because I have many colleagues who won't like this probably. Okay. So a general thought was, we hear a lot about evidence-based medicine, and for me that paradigm seems to be a lot like this classification paradigm, which is here's the thing that gives you this result. And I wish that we would do more of evidence-based model building and then do model-based medicine. Now I realize that's not something that's easy to do in many settings, but at the bedside, which is the kind of domain we're talking about, with clinical data collected on seconds to minutes to hours kind of time scale, it's quite feasible to think of developing mechanistic models, because you don't have all sorts of confounders. If you're looking at the electronic medical record over a 1 month or 1 year period, that subject or patient has gone through all sorts of things, and you really don't have any hope of building a simple model. So, okay, so to just bring it back to the picture that Alex had this morning, I've filled in some of the auxiliary statements that he had on his slide. His slide was nicer, but I think with keeping in mind the example that I gave you, you can start to see how these commentaries on the top-level labels actually make sense. Okay, so Alex's slide went by quickly, but I think this, you could meditate for a while on what he had on those slides. All right, let me not labor that point. Now I want to just quickly zoom through a couple of applications where, again, we've had mechanistic models, essentially as simple as the wind kessel, that have given us some good value. And one of them relates to non-invasive estimation of intracranial pressure. So this is the pressure of the cerebrospinal fluid, the fluid that supports the brain. And it's of great interest to know what that pressure is. But the problem is that the only way you have for accessing it is to drill a hole in the skull and put a catheter or a solid-state sensor through. Really? You don't believe me? People are very interested in non-invasive estimation of intracranial pressure, and they've developed all sorts of proxies for those. But for continuous, non-invasive, patient-specific monitoring of intracranial pressure, I don't know of things. Okay, so we got started on this with my colleague Thomas Helt and a doctoral student some time back, and we started to think, well, this shouldn't be all that different from what the wind kessel is trying to represent. And I'm not going to go through all of this because I'll run out of time, but there are many situations for which you'd like to know, in which you'd like to know intracranial pressure. But because you have to drill a hole in the skull to measure it, the only people who get the actual measurement are those who've got very serious injuries, traumatic brain injury. But if you had a hydrocephalus shunt that failed, or a concussion, or migraines, nobody would think of doing that, of course. If you had a non-invasive way to estimate it, we could start to do some studies. We could imagine having an instrument at the side of the football field that you could pull someone out and take some measurements on. So it is a quantity of interest, but it's very rarely measured. Okay, so the model-based approach, it's again the RC circuit. You've got blood pressure at the entrance to the brain, the middle cerebral artery blood pressure. You've got the compliance of the brain tissue and vasculature. You've got resistance to flow. And one difference is at the far end where the veins are, you actually have collapsed veins because intracranial pressure turns out to be higher typically than venous pressure. So venous pressure might be 5 millimeters mercury, 5 to 8. Intracranial pressure could be in the range of 10 to 15. And so the veins are collapsed. And so there's this interesting effect that goes on, what they refer to as a Starling resistor kind of effect. So the downstream pressure is not venous pressure, it's intracranial pressure. So now you're in business, because if you could measure voltage and current here, or pressure and flow here, it's got information about intracranial pressure. So that's the principle of the thing. Now we can't measure the blood pressure waveform in there, so we take radial artery pressure as a proxy. That's a bit of an invasive measurement, but everyone in the ICU has that. It's a routine measurement. And then instead of flow, we take flow velocity as a proxy. So we use Doppler ultrasound focused on the middle cerebral artery, and that gives you something proportional to flow. All of this is with assumptions, of course. And so here's some examples from our original paper, but Thomas Helt and his students over the last few years have done data collection in multiple hospitals and refined and validated the method to show that these results hold up. So here what I'm showing you is the actual invasive measurement of intracranial pressure in 2 seriously ill patients. Intracranial pressure should not exceed 20. When it exceeds 20, you're very worried. Here you can see it's just out of the ballpark, and this is a patient who died. So here's the estimate in red superimposed. So this is no holes drilled, and actually this is for data that came to us from people at Cambridge University. We had no handle on the data, on the collection. Even the annotations were not very clear. We didn't know if the patients were inclined or flat, because typically with these patients you'll have them sitting up slightly. So none of that was known, and yet it functions fairly well. And the results he's obtained since then, subjects or patients ranging from 5 years to much older, have been very good. So we're excited about that. Very simple model. The other domain I've been spending time on recently, and I'll wrap up with that, is capnography. So this is the measurement of concentration of CO2 in exhaled breath. And there's a very simple tabletop instrument that will measure it. It's very non-invasive. It's just a cannula in the nostril. This big band here is just an elastic band to hold it in place. But it's very easy to put in, and you just breathe normally. And what you'll get is the capnogram, which is, this is 3 different subjects. CO2, when you're exhaling, rises to some kind of a peak level because atmospheric CO2 is essentially 0. So when you start your exhalation, what it's measuring is no concentration at all. And then as you exhale, it's air from the alveoli, deep in the alveoli that's coming out, and that's reflecting actually CO2 in the blood. So you get this typical kind of shape on each exhalation. And the way we got into this was a clinician coming to us to say that he was convinced that there was information in the shape of this that could tell you whether a patient had congestive heart failure or chronic obstructive pulmonary disease or something else. And so that's what we've been spending time on. You can see to the eye, these look a little different. When you start to work with actual data, it's much more mixed up, so it's not canonical like this. But again, a simple circuit model, a simple mechanistic model goes a long way. So this has got 2 parts. One is just the airflow. So you've got a step in pressure when you start your exhalation because the diaphragm relaxes. So there's a step in the pleural pressure. And then you've got flow through a circuit that has some compliance and some resistance. You could model some inductance to capture mass acceleration effects if you want. And then the flow here is carrying CO2. So here's the CO2 concentration circuit. So here's a source that represents concentration in the alveoli. If you remember, I told you that partial pressures, which represent concentrations, function like voltages. So here's the analog. So there's a concentration here. This is the concentration measured at the nostrils. And the interesting coupling now is that the resistance here is the inverse of the flow. It's really the flow that's carrying the CO2. So the faster the flow, the smaller this resistance and the more quickly CO2 in the alveoli appears at the end. Okay, so you can use this model, you can fit it to data, and if you have flow data, you can fit it to flow data as well, so I don't really want to get into all that. I have this slide on pre-processing just to make the point that if you get a typical record, there's a lot of these artifacts in there, and so we spend some time trying to extract what are the good exhalations and ignoring the bad ones, because we're trying to do a fit of this simple model, so we don't want to feed it garbage that we could easily take out. So that again is a characteristic of these mechanistic model building efforts. You take a lot of care with the data, there's a lot of curation involved. You don't just throw the whole thing there and hope that your deep neural net will do the filtering that you need. If there are artifacts that you can recognize and compensate for, you'll do that in advance. Okay, so with this then, actually you get parameter estimates in real time, exhalation by exhalation, parameters for patients with congestive heart failure will tend to concentrate in some part of parameter space. Those with COPD will have parameters in some other part of parameter space. So you can start to use this for classification. Okay, so to wrap up, circuit models are good. And circuit models or any models need to be simple if you're going to try and identify them in real time at the bedside to clinical data. You can't have a full body simulation with thousands of parameters that you're trying to tweak on the basis of very poor data, impoverished data. You hear a lot of talk about interpretable machine learning these days, and a lot of that is sort of sensitivity based. It's trying to figure out which part of the input is most important in driving you to the decision that you've come to. It's not interpretable in the same sense that a mechanistic model is. So I think there's a gap there. What I would like is for us to be teaching machine learning algorithms to discover mechanism. So I think that's a great step. And since I started with the astronomical clocks and so on, I find myself grateful that Newton and Kepler didn't have machine learning to work with. They had to figure out the mechanism and leave the rest of us to struggle with the machine learning. So I'll leave it at that. Thank you.
In this area of medicine, people came up lately with this concept of.
I still need to hear it louder. Yeah.
So, is it better now?
Yeah.
Yeah. So people are proposing an interesting concept right now. Is all these technologies that is at our disposal for monitoring with multiple sensors and wearables, and the concept of digital twins. Like this is, I'm just commenting you on your last saying that the model has to be as simple as possible, 2 or 3 parameters. The dreamers are proposing, okay, you wear, I don't know, 1,000 sensors on you, or it could be even remoteless detection. And like from example, from intelligent toilets where you go and they have embedded a lot of sensors there when you do your needs, and they analyze everything from the stool, urine, and send it away and so on. And with the idea is that you collect as many data that you have from an individual continuously in real time, 24 hours, a similar concept which is used like in aviation industry, where they monitor the engines of every plane in their flight, and they can predict ahead of time if there is a problem. And with the idea that you go from a precision medicine to a precision health. Is that something you think it's like?
I missed what you said about the airplane connection.
So like the idea of these digital twins comes from the aviation industry, where every engine in an airplane has a digital copy somewhere, a model. I mean, it's easy to do because you engineer that engine. You know every single part. It has, I don't know, 1 million parts, but you know everywhere and the interconnection. So you have a digital copy of your engine which functions in real time, and it all receives in real time the data from the engine while in flight. And you can know if there is a disease in that engine ahead of time. Something like that people are trying to propose as an aim in healthcare, that you can do for everybody his own digital twin, and based on this big data and so on. And that's how do you comment, for example, like like coming from your point of view, like trying to have a simple but insightful model compared to like.
So I think if you send it all to the cloud and there's some magic algorithm that's going to classify this patient for you, you'll have to accept whatever answers come back, and the doctor may or may not agree with you. I would much rather see a hierarchical system that works subsystem by subsystem. So some of these sensors are monitoring cardiac health, some are monitoring ability to regulate glucose and so on, and that you sort of have a distributed set of decisions and inferences that then get aggregated into a bigger picture. But taking all that data and not cleaning any of it up, not worrying about differences in time scales for the different phenomena of interest, and just throwing it in somewhere and hoping for the best, I wouldn't want to do that.
Yeah, me neither, but.
Right, the modeling and creation of a similar thing comes from the understanding of what you're modeling.
Right.
Machine learning is very good at discovering things that you did not know that they are related in a way, or finding similarities in random data. They complement each other 100%.
Yeah, well, I don't know, because in the applications I've seen, I don't necessarily see what it's teaching me beyond what the right answer is. Sorry? No, they can learn labels, but what have I learned from it? No, but randomized, okay, they can learn. So the question is, what am I learning from the machine learning algorithm?
If you know a system and you model it with simple elements.
But I had to come with the model, the machine learning. Okay. But that's what I'm saying. I would like to see a machine learning algorithm that looks at the data that Otto Frank looked at and come up with this model. Because right now what we're being asked, I can imagine ways to tackle it. If you can teach an AI system what the characteristics are for flow and pressure and so on, and you can describe the phenomena of interest. I've talked to a couple of students about trying to start something on this side. So if you restrict the domain, there's no reason why we couldn't describe pressures and flows in the body in such a way that an automatic algorithm could say, here are the candidate models. I'm going to limit you to 3 resistors, 3 capacitors, 3 inductors. What are the possibilities? You could do that. I mean, people are not doing that. But I think then the machine learning is focused on extracting a model as opposed to giving an answer. Yeah. Yeah, yeah. So I don't think they're at all, I think they're very complementary, but I think there's insight that we're missing because we're starting to just accept the output of the black box as the final word. And then we go to the next application, the next problem with the next, Mikha. Oh, sorry.
Maybe I'm missing something, but I think the other thing that machine learning is contributing to building models.
Mikha, could you speak up still?
Yes, I'm saying that the other thing that machine learning is contributing to models or can contribute to models is finding factors that are correlated. And then you still need to put your denominator, or you need to put the power to try to build a real equation and say how much this contributes to the outcome. But there's always new things that you think that are not correlated that you find that are correlated.
I agree. So for instance,
so just to dismiss it is wasteful.
No, so I really I value the focus on interpretable machine learning models because they're telling us in some way, based on, I think, sensitivity type calculations, what the important variables are, and then you can start to look at those separately. But they're not teaching us mechanism by just...
Hi, George. Thanks for a very interesting and stimulating talk. So, yeah, I completely agree that actually the kind of physical laws cannot be learned in a lot of situations because there are confounding factors. And it's funny that you mentioned Newton on your last slide, because if you were to try to learn gravity, I don't think it will be possible because you will get a very complicated formula that's both the gravity, but air resistance and the shape of the object and all that. So you won't get it. This being said, there are recent works that show that there are fairly subtle algorithms that can be learned, like sort of, like maximum online matching type algorithm, that you can create a black box that does the right algorithm.
Okay.
The box somehow, I don't know if the box, how the box works, because the box...
So for instance, there are procedures, I believe, that search for good features for machine learning. Now, in those features, the particular nonlinear combinations they choose, you might see clues to what you want for your model.
So here the features are complete, right?
Yeah.
Because basically you are saying, here are your edges come in and they have those weights, and here is a loss function and all that. So if the features are complete, and that's a human decision what the relevant features, and they are complete, I think that the jury is still out. But you might not be able, the model inside, how would you assert? So my question ultimately is, how can you assert if your black box discovers the mechanism or not?
Yeah, so actually, I mean, how do you assert that your model is good or not? It's really how productive it is in allowing you to explore new things, and
Actually, I think this way. I mean, the human body, I'm a medical doctor.
Yeah.
Human body is a complex system. So to model it, you need huge amount of data. Because I also think, like this gentleman, I mean, there's so much hidden data, so much hidden interactions, so much hidden relations. Machine learning can be utilized to actually explore or demonstrate. Yeah,
well,
that's
actually,
hidden relationship. Because you know what I mean, if you make medical research, even to end up with a good research idea can be a problem.
Yeah, so we have no lack of complicated models in the medical domain and physiology. For instance, in modeling cardiorespiratory behavior, there is this elaborate model called NUMA, which is based at University of Southern California. It's got many subsystems which were isolated in different studies. Parameter values were obtained in different studies. This whole thing has been put together. You've got a very high order model representing the interaction of the heart and the lungs, and covering things like sleep apnea, exercise at elevation, all sorts of things. It's a monster of a model. It's great for simulation. There's no way to make it patient-specific. You just couldn't do the experiments to fix all the parameters in that model. So it's not clear how helpful it is to you clinically. It's helpful in a general way to get a sense of what the range of behaviors might be. But if you want to actually get a model fitted for a patient in front of you, you cannot, your data is not rich enough to support identification of such a large model.
I can have a...
There is one more question from Bart. Yes.
Yeah, I can give one more comment. I think the very deep way is if you compare models with AI, that is that you, for the first time, we always looked at features and we looked at models, but that's very local. That's actually in a point that you say we have a description of what happens in that point if you talk about edges and features. And now for the first time we use context, and that's a major thing. So we can look at how is it embedded in a larger structure. So we look, how are these edges grouped inside of a nose, etc. So that's exactly the trick. While we have deep learning, we always had neural nets. We had just input layer, hidden layer, and output layer didn't work. But now we have incremental context. And that means we take far more information. So we don't look at one vessel that we describe with an I formula. That's a local description, pressure, volume, really nice. But we have now a vessel that is embedded in many other vessels, in the circle of Willis, etc. And we see the whole system produced. For a long time we were fighting, how can we go from local vision, early vision, front-end vision, you know it, to higher level vision. And for the first time we can now do this. We don't have formulas for that yet, and the next decade we'll see a lot of development. But incremental contextual processing is completely different from local modeling features. And that's the gain we make now.
Well, I mean, you know, I'm in awe of what machine learning can do as well. And I'm glad lots of people are working on machine learning, because I know I want to stay with the mechanisms. So. Okay.